All right, well, today we're going to attempt to do the mole concept. I have a bit of a cold, but I'm doing my best here. The mole concept. This is a mole, kind of a funny looking sort of animal, impaired vision because it lives underground, whatever. Did manage to make it into a movie in 1956, The Mole People. The mole person that we are going to be interested in is this guy, Amadeo Avogadro. You have to admit he really looks a little bit like a mole. Whatever. But before we get started, we have an exam coming up. So let me just review this for you one more time. Academic Success Center, here's their email, there's their phone number, and they're in A100, the basement underneath the library, I believe. They do tutoring by appointment, drop-in, or virtual online, Monday through Friday, 8 to 8, Friday, 8 to 4. They're actually pretty good. I've had lots of people come and have success stories from them. I have a few of the little handouts up here. If you don't know about them, they're worth looking at. We have Lab 4 on Wednesday. The lab that's on Blackboard is the current lab, so that's good. A week from today, we will do the sample exam. Remember, go to Blackboard, print 2 copies of the sample exam, work 1, hand it in, 10 points extra credit. Keep the other one with you for taking notes. When we do the sample exam in class, it will, number 1, be a short lecture, because it's so simple. And number 2, we will go over all the questions. When we finish the lecture for the sample exam, quiz 1 will magically appear on Blackboard. It's worth 20 points. You must complete it before the exam. Any questions? All right. We have pointed out that atoms are incredibly small. Single pure copper penny would be about 28 sextillion. In order to help chemists deal with these huge numbers, we have invented a unit. The unit is called a mole, and it contains 6.02 times 10 to the 23rd things. It's a unit. Because it's a unit, you can have a mole of anything. You can have a mole of atoms, a mole of molecules, a mole of students, a mole of whatever. Just a unit. Came about through the work of Avogadro and others. He kind of stole this data from other people too. But what he observed was that equal volumes of any gas contained the same number of gas particles. Well, that was a real surprise. It still is to some extent. Further, if you had 22.4 liters of any pure gas, the mass of that gas matched the formula mass of the element or compound. Now, that was even more surprising. And this is the fundamental thing that allows us to do quantitative calculations in chemistry. The number 6.02 times 10 to the 23rd is called Avogadro's number in his office. What this basically means is that a mass equal to the formula mass of anything will contain 6 times 10 to the 23rd particles, That's 1 mole. The formula mass in grams is called molar mass. Now, what's a formula mass? Simply the sum of the average atomic masses of everything in the molecule. Technically, the units are atomic mass units, AMU, but formula mass generally is presented without units. For example, if we had glycine, this is the amino acid glycine, C2H5NO2, and I asked you what the formula mass was, you would look at your periodic table and say, okay, carbon weighs about 12.01. We have 2 of them. 5 hydrogens, a touch over 1. 1 nitrogen at about 14, and 2 oxygens at 16 each. Do all the multiplication, add up all the numbers, and you get 75 for formula mass. To make this into a molar mass, all you do is express this in grams. So if we have 75 grams of glycine, it will contain 6 times 10 to the 23rd glycine molecules. It's an amazing concept. It's also very useful for the quantitative chemistry that we will do. This is a balloon containing 32 grams of oxygen. This is a little lump of copper weighing 63 grams. This is 18.02 mils of water, and this is about 100 grams of calcium carbonate. Each of these masses contain 1 mole, and they all have exactly the same number of particles in them. So if you wanted to react oxygen and copper in a 1-to-1 ratio, you would take 32 grams of oxygen, 63.5 grams of copper, and it would be 1-to-1. Now, today, 12 grams of the isotope carbon-12 is used to define what a mole is. Instead of simply saying 6 times 10 to the 23rd, the definition today is that it's the amount of any substance that contains as many particles as there are in exactly 12 grams of carbon-12. Not carbon, but carbon-12, the isotope. So that's the modern definition. Now, the mole, once again, is a unit. And if you have any difficulty remembering that, here's something to help you remember it.
Is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high it reacheth into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. And a mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mold of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and, of course, block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating one marshmallow each second. Not two, because that'd be cheating. With 5 billion people munching, how long you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. But say you had a mole of atoms, would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You can hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
Mole Day. What do you think Mole Day is? October 23rd, 10/23. How about that? And it's coming up. We get to celebrate it in class. Couple points this little silly thing tried to make. Number 1, mole is just a unit. You can't remember, you can't forget that now. It's embedded in your brain. And number 2, it's awfully big. It's a huge number. Let me do a couple more things. They pointed out a handful of stuff. Well, this is glycine. This is 7.5 grams of glycine. That's a mole of atoms. As huge a number as it is. Let's just do one more. Gosh, that's a big number sort of thing. This is a leaf. You're 10 centimeters above this leaf. What we're going to do is back off one factor of 10 at a time from our leaf and see what we see when we finally get to 10 to the 23rd. Okay? Simple. And there's no saying. We're a meter above, we're 10 meters. We're now 100, and then 1,000. 10,000, blah, blah, blah. We can see that's, it's in Florida. How about that? And it's on Earth. There's Earth. There's the moon going around it. There's our orbit. Still in orbit. There's the sun. We're backing away. We're at 10 to the 14 now. That's the sun, that little spot. It's gone. We are now in deep space. Oh, stars. How about that? That's the Milky Way. This is one of the branches, one of the arms. And now you can see it at 10/20 seconds. And at 10 to the 23rd meters above our leaf, the Milky Way is this little fuzzy blob. Again, it's a phenomenally large number, reinforcing just how small atoms really are. Any questions? Let's do a couple silly exercises here to try to stress just what we mean by being a unit. Okay? Whenever you think of mole, it's the same thing as a dozen. It's just a big, very big dozen. Okay? 6.02 times 10 to the 23rd. We have 23 decimal places here. We tend to round this in all of our calculations to 6.02 times 10 to the 23rd. That's three significant figures. Again, you can have a mole of anything. A dozen bagels is 12. A mole of bagels is 6 times 10 to the 23rd bagel, just a unit. So let's do this in a problem. Silly problem. We have four-legged dogs. We have 66 dozen of them. How many legs? Okay, we can do this because we have two ratios that we know. There are 12 things in a dozen, and there are 4 legs in every dog. So we'll take our given here, which is our 66 dozen, and we're going to multiply it by two ratios. 12 things in a dozen and 4 legs in a dog. We've set these up with dozen and dog in the denominator, so dozen will cancel and dogs will cancel. Now to get the answer, 66 times 12 times 4. A little over 3,000 legs. Okay, we can do that, right? Change the problem just a bit. We now have 66 moles of dogs. How does that change the calculation? We know there are 6 times 10 to the 23rd things in a mole instead of 12 in a dozen. We still know there are 4 legs in a dog. Take our given, multiply it by this ratio and then the dog ratio. Again, both of these are at the denominator, and they cancel. Calculator gives us this. If you happen to have your calculator handy, you can pull it out and just make sure that in fact you can do this simple calculation. We are dealing with 3 significant figures, so we round this to 1.59 times 10 to the 26. Any questions? All right, well, let's do a couple real problems. We have a mole of hydrogen gas. By definition, it contains 6.02 times 10 to the 23rd hydrogen molecules. How many molecules in half a mole? That's simple, it's just half of it, right? Well, let's do it the long way. Again, 6.02 things per mole. 0.5 hydrogen, 0.5 moles of hydrogen is our given. Start with that. Simply put in this ratio with mole in the denominator. Moles will cancel, and we're left with only molecules. 0.5 times 6 times 10 to the 23rd is 3.01 times 10 to the 23rd. Remember, we're doing the math on the coefficient, not the exponent. Any questions? All right, let's just quickly diverge here for a second and look at chemical formulas in terms of what they mean for mole ratios in a compound. If we have CO2, we write the formula CO subscript 2. That tells us it contains 1 carbon, 2 oxygens, the ratio is 1 to 2. This ratio is also called to mole ratio, 1 to 2. There is 1 mole of carbon and 2 moles of oxygen per mole of CO2. If we had ethanol, this is the alcohol of consumption. This has 2 carbons. It has 5 hydrogens and 1 oxygen. The mole, 6 hydrogens, I'm sorry. The mole ratio is 2 to 6 to 1. Simply the subscripts all added together. Here we have a compound. 2 moles of iron, 3 moles of sulfate. What's the formula? Let's just take our iron and our sulfate, put it down. Now we have 2 moles of iron. We have 3 moles of sulfate. Exam is coming up. What would you name this guy? Well, we say to ourselves, it's ionic, it has a metal. We don't use multipliers. So it's going to be iron sulfate, except iron is a transition metal. So what's the charge on the iron? Well, sulfate is -2, and we have 3 of them. That's 6 negatives. Each of these ions must be +3. Iron, 3, sulfate. Just one more quick one. 3 carbons, 6 hydrogens, 2 oxygens. We have CHO, 3 carbons, 6 hydrogens, 2 oxygens. Now we're going to use mole ratios to allow us to talk about the parts of molecules. For example, if I asked you how many atoms of hydrogen there were in 1,000 moles of ammonia, NH3. Well, we know there are 6 times 10 to the 23rd molecules in a mole. That's good. We also know that in every molecule of ammonia, there are 3 hydrogens. That's the mole ratio. 3 hydrogens for every ammonia, 3 to 1. So, starting with our given, we will put in this ratio and the mole ratio. Again, we put mole in the denominator. 3 hydrogens for every molecule. Moles cancel, molecules cancel, and we're left with atoms. Once again, if you have your calculator out, 1,000 times 6 times 10 to the 23rd times 3 gives us about 1.8 times 10 to the 27th atoms of hydrogen. Now, I try to be very careful when I make my slides so that everything cancels like it's supposed to. What if, instead of writing this ratio properly, you had written it this way? You would immediately look at this and say, well, that's not right. Mole is not going to cancel with mole. They're both in the numerator. What do? Just take the ratio and flip it upside down. Now everything cancels nicely. The bottom line, if you write a ratio upside down on one of these things, just flip it over. Mathematically, it's a valid operation. Any questions? Let's do another one. Carbon tetrachloride. How many chlorine atoms in 0.05 moles? Once again, we can say if we had a mole, that would be 6 times 10 to the 23rd carbon tet molecules. We look at our mole ratio here. 4 chlorines for every carbon tet molecule. 2 ratios. We take our given, multiply it by molecules per mole, and then multiply this by 4 chlorines per carbon tet molecule. Moles cancel, molecules cancel. The math, 0.05 times 6 times 10 to the 23rd times 4, 1.204. This is a calculator answer. We're dealing with how many significant figures here? 3 and 3 here. How about the 4? That's an exact number. It doesn't count. 1.2 times 10 to the 22nd. A favorite question for exams and stuff. We have so many moles of a gas. How many particles is that? This is not only a good thought question, but this tests if you can use your calculator. Right? Set up a simple ratio. We know that there are 6 times 10 to the 23rd particles in a mole. We have 3.27 times 10 to the minus 9 moles. That's our given. Here's our simple ratio. Moles will cancel, and we get particles. Now, let me point out, I have deliberately spelled moles out here, M-O-L-E-S, and used the abbreviation M-O-L. They're all the same. M-O-L-E, M-O-L-E-S, M-O-L, same thing. They all cancel. 3 times 10 to the minus 9 times 6 times 10 to the 23rd. We're left with 1.97 times 10 to the 15. Even though we have a nanomole, 3 nanomoles here, we're still talking 10 to the 15 particles. It's amazing. All right, there are 3 mole tutorials in this chapter. And this is the last chapter before the exam, so there are 4 tutorials total. 3 of them have to do with moles. This is mole mass relationships. It appears just like this on Blackboard. Some of the Blackboard problems are a little more complicated, and we'll actually do a couple more of these a bit later just to show you what I mean by that. But okay, we have, what is this called? Potassium. NO2 is nitrite. We have 1.1 moles of potassium we're looking for how many moles we have total. Well, this is simple, because there's one potassium per molecule, right? So it's a 1-to-1 ratio. I just want to show you how you know how to set up the ratio though. As you look at this, our given is 1.1 moles of potassium. So moles of potassium has to be in our denominator. Up here, moles of potassium over moles of potassium nitrite. 1-to-1 is our ratio. Simply multiply that by 1, and we get 1.11. Let's do one with a non-1 ratio. This is water. It contains 1.34 moles of hydrogen. How many moles of water do we have? Once again, our given is moles of hydrogen, so that has to be in our denominator. For every mole of water, we have 2 moles of hydrogen. The ratio is 1/2, 1/2. Simply take our given, multiply it by our ratio, and we get 0.671. Any questions? All right, let's do a real exam question. We have magnesium hydroxide. It's an antacid, also a beta laxative. We have 17.8 grams of it. The formula is Mg, which is a +2, and this is hydroxide. Hydroxide is a -1, so we have 2 of them. Magnesium hydroxide. And here's the molar mass, 58 grams per mole. All right, so how many moles in 17.8 grams? Well, this is going to be our given. And this is going to be our ratio. How is that a ratio? Just like we said density was a ratio, mass divided by volume. This is mass divided by the number of moles. So we can set it up like this. Here's our given. Here is our ratio, 58 grams per mole. We have to put our grams in our denominator. So grams will cancel. So all you do is you take 17.8 divided by 58.3. What do you get? About 0.3. Now I want you to think about what we just did, because this is a useful thing to remember. You could write it on your hand, you could write it on your 3x5 card. It's useful. We took a mass and we divided it by the molar mass. What did we get? Moles. Mass divided by molar mass is moles. Useful thing to remember. So useful that I'm saying it twice. Mass divided by molar mass is moles. Any questions? Later in this chapter, we're going to deal with percentages, percent composition. I put this one in just to introduce the notion of what percent really means. A mole contains 6 times 10 to the 23rd molecules. What is 10% of the mole? Well, we could use our calculation, our algorithm, Here's our given for the ratio. When you see 10%, the little sign here like that, what that means is actually 10 divided by 100. It's a ratio. So, if we take our given, multiply it by our ratio, no units, simply 6 times 10 to the 22. Now, if you're paying attention, nothing turned yellow. 6 times 10 to the 20, that's not it. 1 times 10 to the 22, well, the exponent's right, but not 1. 0.6 times 10 to the 22, first of all, that's bad form. And secondly, that's wrong. None of these are correct. On your exam, you may have one or more questions with the dreaded none of the above. So just always be aware of that. Any questions? Well, let's do another simple one. Here I have 21.5098875 grams of CO2. Its molar mass, 44 grams per mole. How many moles is it? Well, we know the mass. We know the molar mass right here. Remember what we just said? Mass divided by molar mass gives us moles. Again, it's a very useful thing that comes up all the time. So, there's our mass, here's our molar mass. Simply divide them. What do we get? We get 0.48875 as our calculator answer. Now, this has a dozen significant figures, but our molar mass only has 4. So we have to round this. Does this go to 0.4888 or 0.4887? It ends in exactly 5. There's a rule for this. The rule is simply you round even. If it ends in exactly 5, you round even. That way you're rounding up half the time, down half the time. So this rounds to 4888. Remember that. That is useful to remember too. Another exam question. I put this table on the exam so you didn't have to mess with the periodic table. And I say we have 1.03 moles of methane, carbon tetrahydride, right? Right. Calculate the mass of this stuff. Well, we know the number of moles. What we need is a molar mass. So this question really had 2 parts. Do you remember how to calculate a molar mass? Carbon is 12.011. Every hydrogen is 1.0079. So we have 1 carbon, 4 hydrogens. This is the molar mass we're dealing with, 16.0426. Keep all the significant figures until you're done, and then clop them off. So here's our molar mass, here's our number of moles. we write the number of moles. We want moles in our denominator. We want grams of methane in our numerator. Moles. This is 1.03, and this is 16, well, that's 1.03. This is 16 per mole. Simply multiply these out, and we get this guy. Now we look at our significant figures. 1.03, so that's 3 of them. Round this to 16.5. Any questions? Well, the second tutorial dealing with this is this one. It's a table. Everybody loves tables. As you go through new problems, you'll wind up with something missing in every one. Simply calculate. To do these, you need to remember fundamental definition. And that is molar mass is simply mass divided by moles. Here, we're looking for molar mass. We are given mass, we are given moles. We simply divide them, and we get 100. So 3 significant figures. Let's do it again with mass missing. Again, if I had a 3x5 card, I would just write the basic expression down. Molar mass is moles divided by mass, and just work from there. If you do, you'll see that mass is simply moles times molar mass. Here's our moles, here's our molar mass. 163 is our number. Any questions? Dreadfully simple. Here's the same type of problem in another tutorial, mole mass conversions. In this guy, you're given a number of moles, you're given grams, you're trying to figure out moles. Here's our molar mass. What do we have here? We have a mass and a molar mass. See, it is useful. Mass divided by molar mass is moles. Simply take our mass and our molar mass, divide them out, and it's 1.38. Any questions? The same problem as the table, except different. We have 0.2 moles of lead. Here is molar mass. We're looking for the mass this time. Mass is going to be moles multiplied by molar mass. So moles multiplied by molar mass, 19.9 grams. Exactly the same types of problems. Now, I put a couple more of the mole mass conversions in that aren't quite as simple as the first couple we did, because they are on, oh, I forgot this one also shows up. We have an element with a mass of 29. That 29 grams represents 2.7 moles. What's the element? Well, molar mass is mass divided by moles, right? We have a mass, we have the number of moles. With this simple relationship, we can calculate the molar mass of this element. We simply divide them, and we get 10.8. Now, on the exam, you will get a periodic table. You may rip it off, take it home as a souvenir, all that stuff. It'll look something like this. What you're looking for is an element with a molar mass of 10.8. Now that's going to be, for an element, the same as the average atomic mass, isn't it? So, 10.8, huh? Well, let's see. 6, 9, oops. How about that? We're here already. 10.81. This is boron. So what do you do with the tutorial and on Blackboard? Because there's some on Blackboard too. You just put the B in. Any questions? All right, more problems. We have 10 to the 20th molecules of chlorine. What's the mass in grams? We know how many molecules we have, and we're just looking for the mass. We could do that simply if we knew how many moles we had, right? So we have 10 to the 20 molecules. We know if we had a full mole of it, it would be 6.02 times 10 to the 23rd. Therefore, there's our given. Our ratio with molecules in our denominator, 1 mole, 6 times 10 to the 23rd molecules. Molecules cancel. Oh, and we're going to multiply this then, once we know this gives us number of moles, and this is grams per mole. Mole in the denominator once again. Molecules cancel, moles cancel. We're left with grams of chlorine. Do the calculation. 10 to the 20th divided by 10 to the 23rd. We get 0.011777. The two significant figures, that's what we have, right? It's 1.2. Times 10 to the minus 2. All right, before we leave the realm of way too many calculations and get on to something that's a little more fun, let's just do a couple more of these guys. Lithium nitride contains 1.9 moles of lithium. How many grams of lithium do we have? So this is a two-step process. We start off here. Our given here was moles of lithium. So that's in our denominator. Our ratio is therefore 1/3. We're going to take the ratio, multiply it by our given, that's the number of moles, and we get 0.66 or 0.633 moles of lithium nitride. How do we get grams? We know the molar mass of this, it was given, it's hidden, 38 grams per mole, 34.8 grams per mole. Simply multiply these together, 22 grams is our answer. So again, this problem differs from the first one. You have to do this part first, but that's not your answer. have to do this times molar mass to get your answer. Any questions? All right, well, let's go ahead and skip forward to analysis, proportions, and the mole. This is a classic SpongeBob moment. Percent composition. If I ask you the mole ratio of hydrogen to HCl, that's trivial. One hydrogen in every HCl. Expressed in moles, 1 mole of hydrogen for every mole of HCl. Right? But we can write this another way. Because we know 1 mole of hydrogen, right here, has a mass of 1.008 grams. We can figure out the molar mass of HCl, that's that plus 35.5. We get 1 gram of hydrogen over 1 mole of HCl expressed as mass. Okay, well, that's nice. We can do that. That's 1 mole. This is 1 mole. We're good. But what if we do this math? What if we take 1 divided by 35? We would get 0.0284. That's the fraction. If we now take that and multiply it by 100, we get the percentage. We can therefore say HCl is 2.8% hydrogen. That's percent composition.
The number in the denominator, the 35.45,
Yeah.
now that's just CL though, right? Because I'm just confused on how you're getting the bottom number.
Oh,
I
we're
thought it was
adding
gonna
it. Go to the periodic table, look up the average mass of chlorine, average mass of hydrogen, add them together.
Wouldn't it be 36?
It would be. You're
Okay.
right.
Okay.
You're right. I always forget to change this slide, even though I know darn well somebody's going to catch me someday. Anyway, yeah, that's a mistake. Anyway, 2.8% hydrogen. If we have calcium fluoride, what's the percentage of fluorine? Calcium is group 2. There's 1 plus 2, and this is 2 fluorines at minus 1 each. So, our mole ratio here, we have fluorine at 19 grams per mole. Calcium fluoride, I believe, is 78 grams per mole. We're going to convert this and call it a mass ratio. We will use mass ratios again later in the semester. But for right now, 2 moles of fluorine is the same thing in terms of mass as 2 times 19 grams. Calcium fluoride, 78.08. So our mass ratio is simply this. 2 fluorines at 19 each, divided by 78 for calcium fluoride. Okay, 2 times 19 divided by 78, 0.4867. We are looking at 4 significant figures here, 4 significant figures here. That's 4. To make this as a percentage, you simply multiply that by 100. 48.67%. Calcium fluoride is roughly 48-49% fluoride by mass. Let's do another one. Here we have a compound. SC. What is SC? Oh, there it is. By George, that's a transition metal, isn't it? That's bad news. What is ClO3? It's the parent of the chlorine group, right? So it's a chlorine. We have 3 of them. These are -1 each. So this is scandium. The charge must be +3 to make it neutral. We write it scandium 3 chloride. Again, exam in 2 weeks. All right. We're looking for oxygen and scandium 3 chloride. We have 9 oxygens, don't we? Oxygen weighs about 16 grams per mole. This stuff, 295. Quickly, write the mass ratio. The mass ratio, 9 oxygens for every scandium 3 chloride. We convert this to mass now. 9 times 16. And here's our 295. Percentage of oxygen. We're just going to multiply this out. We get 48.488. And that times 100, 48.8%. Any questions? Let's do one more. Fluorine and magnesium fluoride. We have 454 grams of magnesium fluoride. What's the mass of that? What's the mass of fluorine in a pound of magnesium fluoride? Well, first we need to figure out the percentage, right? We have 2 fluorines for every MgF2. Fluorine is 19, MgF2 is 62. 2 times 19, and here's this. Now we could convert this directly to a percentage, multiply our 454 by the percentage, or we could save ourselves a step and say, wait a minute, there's my given, I need a ratio. That's a ratio, right? Sure it is. Take our given, multiply it by a ratio, magnesium fluoride cancels, we're left with grams of fluorine, which by the way is what we want. 454 times 2 times 19, we have about 277 grams of fluorine. All right. right, there is one more tutorial for the chapter, your very last for the first before the exam. It is percent composition by mass. Okay. In this one, we are given something. We want to enter the mass percentage for each of the elements. Okay? First of all, what is this? What is ClO? Chlorine family minus 2 oxygens, hypochlorite. Nickel, transition metal. Each of these will be minus 1. This is nickel 2 hypochlorite. And that's how much it weighs. All right, to calculate each of these, you're going to look at your molecule and do a mass ratio. There's 1 nickel at 58 divided by the whole thing, which is 161. So, for nickel, 58 divided by 161 times 100, 36%. For chlorine, how many chlorines do we have? 2 of them. 2 at 35 divided by 161 times 100, 43.9. Oxygen, how many oxygens? Just 2. 2 times 16 divided by 161, 19.8. Now if you notice, these don't quite add up to 100. That's just the way the computer rounds, I'm sorry. The lesson though, I had a student once on an exam, looked at a problem, did the first 2, said, I'll just subtract it from 100. Wasn't quite what I was looking for. I'm much more lenient than Blackboard is. Blackboard will write you wrong. So please, just do them and put down whatever you get. One more. ClO2 is what? All right. We have 2 of them. Calcium is not a transition metal, so this is just calcium chloride. We have 1 calcium. It weighs 40 divided by 175. 1 calcium at 40 divided by 175. Let's do it. 40, we have 1 of them, 175, 22.9%. We have 2 chlorines at 35.5 each. Divided by 175, 40%. And finally, how many oxygens?
4.
We have 2 times 2 is 4 oxygens. 4 times 16 divided by 175, 36%. This time it added up to 100. Any questions? All right, you can take a breath. We are done calculating. Now we're going to do fun stuff. We made a ball and stick model in Lab 1. I just want to go over models a little bit because you'll see them a lot. This is a ball and stick of the amino acid glycine. It has a nitrogen with 2 hydrogens, 2 carbons, 2 oxygens, total of 6 hydrogens. This is called the space filling model. This gives a much better approximation of what the thing really looks like. The disadvantage here is this is a carbon-oxygen double bond. You can't feel that here at all. Okay. How did I know that this was carbon? Because it's dark. Okay? Typically, carbon will be shown as black, hydrogen white or gray, oxygen red, nitrogen is blue. Just convention. Diatomic elements. Make sure you have a good feel for these guys. Hydrogen, nitrogen, oxygen, and these are all the halogens. So group 7. Group 7 halogens are all diatomic. That's the way they exist in nature. So does hydrogen, nitrogen, and oxygen. In terms of models, hydrogen will be shown as this, nitrogen blue, oxygen red, fluorine kind of a yellowish green, green for fluorine, brown for bromine, and finally purple for iodine. You try to come up with colors that more or less match the element the way it looks. So for sulfur, for example, you would do yellow. For something like, bless you, aluminum or West silicon, you have no clue what that looks like. You just stick in anything. But the basics are pretty simple. Molecular formula. We use the atomic symbol for a compound, just as an abbreviation of what it is. Again, this is glycine. This has 2 carbons, 2, 5 hydrogens, 1, 2, 3, 4, 5, 1 nitrogen, and 2 oxygen. This, now you can see the double bond. If we were to write the molecular formula, we could just simply say C2, H5, N, O2. Now that gives us the ratio of all the atoms. We can do mole ratios and stuff like that. But it tells you nothing about what the molecule looks like. So it's useless as far as that goes. We can make it more useful by writing it slightly differently. We can look at this and say we're starting off with a nitrogen with 2 hydrogens. That's bonded to a carbon with 2 hydrogens. And that's bonded to this group, which is a carbon, 2 oxygens, and a hydrogen. So if you look at this, you know exactly, pretty much, what you're dealing with. The ultimate is called a Kekulé structure. Here you would show all the bonds of NH2, bonded to CH2, bonded to COOH. These are a pain. The other one is much more useful. So this is molecular formula. Very simple. There's one other type of formula convention that we need to know about, and that's called an empirical formula. Empirical formula is the lowest whole number ratio of elements in a compound. This is glucose. Glucose is a sugar. We have 6 carbons, 1, 2, 3, 4, 5, 6. We have 12 hydrogens, the little gray things, and we have 6 reds, the oxygens. The lowest whole number ratio. You look at this, decide which one is the smallest. That's a 6. So 6 divided by 6 is 1. 12 divided by 6 is 2. And 6 over 6 is 1 again. CH2O is the empirical formula. Lowest whole number ratio of elements. The problem with an empirical formula is that it is ambiguous in terms of the structure. This is acetic acid, the acidic component of vinegar. It has 2 carbons, 4 hydrogens, 2 oxygens, and its empirical formula is CH2O. Why do we even care about empirical formulas? Well, one of the things that you do in chemistry, and we will do this in chemistry lab, by George, is to determine analytically the empirical formula of a compound. When you do chemical analysis, the result you get is the empirical formula. So that's why it's useful. In order to get a structure, you need to know something else about it. Any questions? Well, let me show you something neat then. Here's our glucose. There's a beaker of glucose. Turns out that if you add concentrated sulfuric acid to a sugar, this will catalyze the decomposition. Now our empirical formula here is CH2O, right? This will break the sugar down to carbon and water. Let's watch. This is something you do very carefully. Concentrated sulfuric acid eats skin instantly. Don't want to do that. Stir it up very carefully and let it sit. After a couple minutes, it starts to turn blackish. After a few more minutes, it starts getting really hot. Starts to bubble. Here comes the water off as steam. And what's left over? The carbon. Breaks down to water as steam and a cute little column of carbon. Isn't that kind of neat? Now, think about this for a second. We're dealing with sugars, aren't we? Sugars are called something. They're called carbohydrates. Why? Carbohydrate. Carbon and water. Carbohydrate. Let's do some quick empirical formulas. Acetylene, welding gas. Formula C2H2. CH is our empirical formula. This is what acetylene looks like. We have a carbon-carbon triple bond in terms of a model. Here's our triple bond. Again, you can't tell it. It's a space-filling bottle with the hydrogens on each end. Benzene, C6H6. 6 is our lowest number. This is also CH. This is what benzene looks like. Benzene is the heart and soul of organic chemistry. It's sadly hepatic neurotoxin. But nonetheless, it's a wonderful molecule. Alternating double single bonds that really aren't. The molecule actually looks something like this. Our double bonds are in this cloud of electrons above and below the plane. Nice flat molecule, really cute. Empirical formula for water. We have one oxygen, 2 divided by 1, 1 divided by 1, it's H2O, isn't it? And finally, hydrogen peroxide. Divide everything by 2, you get O. All right, that's it for chapter 4. Let's think about what's going to happen the next 2 weeks. On your syllabus, this is week 6. First of all, we will not have class on Wednesday. On Monday, we will do exam 1 review. Please remember, print the sample exam, work it, hand it in on Monday. 10 points. As soon as we finish the review here, quiz number 1 will appear magically on Blackboard. 20 points, do it. It must be completed before exam 1. So you have a week. On Wednesday, go to Blackboard. You will see something called Lab 5. It's a nomenclature review sheet. It's got maybe 30, 40 compounds on it. And you look at them and you write the names. Over and over and over again. What this is practice. Practice for the exam. So print this guy at home. Work it at home. Don't come to lab. There is no lab. On the morning of the exam, hand it in. That's how you get your 10 points for the lab. All right.
You say you'll open that up, the sample next week?
The sample exam, yeah, soon I'll open it. The next week is exam week. Exam 1 in this room, normal class time. Remember your calculator. Remember your 3x5 card. Now, most people, honestly, will finish this exam in 20 to 30 minutes tops. All right? And there are a couple people that have testing accommodations. If you want to, you can sit here for 2.5 hours and complete it. So you have all the time in the world to do it. If you need more accommodations than that, please send me an email. Wednesday, once again, there is no class. Now, this is not my doing. This is departmental doing. It's called Lab Makeup Day. Think of it as a snow day, even though it's not snowing. It's very hot. It's a day for the entire class if we all missed a lab. Then we would go in on this day and do it. Hasn't happened, not gonna happen, it's just a day off. So we do the exam, 2 Wednesdays in a row, we don't have class in 204, and then we get back to normal. Once we have completed the exam, all the tutorial content, for the first 6 weeks disappears. You will never see it again. Well, maybe once, but you won't see it again. Okay? So make sure you get it done before we take the exam. Speaking of tutorials, here's our list. Today we added moles and mass, mole mass conversion 2, mole mass formula, and percent composition. There's lots of them, 5 points each. Please get these done. Any questions? All right. I hope. Yep.
Just this one.
There's lab this Wednesday. The following 2 we don't have lab.
Very good.